Hi, I'm Rick Derbyshire, and today I will be giving you a brief overview of our paper, ICS Testbed Tetris, Practical Building Blocks Towards a Cybersecurity Resource. The paper was a collaborative effort between the 7 authors listed here, all of whom are members of the Security Lancaster Institute at Lancaster University in the United Kingdom. The core focus of this work is around the creation of a high-level flexible model used to support industrial control system testbed design. However, I will first provide an introduction into industrial control systems before describing related work in this space. This helps set the scene with regards to the challenges we hope this paper addresses. I will then move on to some initial design considerations based on our previous work, before introducing the experiment lifecycle, which is used to support discussions around our model's construct and use. I will then cover the model before breaking it down into building blocks, providing a bridge between what can be considered a theoretical concept and development activities. This forms a structure to then describe our baseline practical implementation options, before introducing the concept of an online living resource and its future integration with the Tide H platform. For those of you who are unfamiliar with industrial control systems, they are essentially a set of computational resources used to monitor, control, and automate industrial processes. Some of these underpin elements of critical national infrastructure, including water treatment and energy distribution. The figure here is Cisco's extended version of the Purgey Enterprise Reference Architecture, commonly known as the Purgey Model. This is often used to provide a high-level view of an industrial control system's fundamental features, separated into distinct zones. A safety zone to manage safety functions, a manufacturing zone to monitor, control, and automate operational processes, a demilitarized zone to provide a buffer between the manufacturing zone and the enterprise zone, and finally the enterprise zone, providing IT services and access to operational data via the demilitarized zone. In order to explore in-depth ICS cybersecurity challenges, testbeds are an essentials tool, avoiding the need to experiment exclusively on live systems, making work in this space extremely important across the cybersecurity community. Over the last 6 years or so, the Security Lancaster Institute has been involved in the design and build of ICS testbeds. This has included links with both public and private sectors through collaborative engagement. As you can see from the list provided here, we currently have 5 existing publications in this area. These span a number of themes, from design considerations to lessons learned. However, if we look more broadly into this space, we can typically categorize existing work into 3 topic areas: surveys, theoretical concepts, and practical implementation. All of these add value to those looking to develop their own testbeds, but don't provide a single point of reference. We often find that surveys are quite high level and abstract. Theoretical concepts can be rigid and unclear from an implementation perspective, and practical implementation work can be narrow in scope, often aligned to how the authors have built their own facilities. These are the challenges that we wanted to address in this paper through the introduction of a high-level model and associated implementation guidance. Before moving on to our high-level model, it's worth exploring key testbed characteristics you may wish to consider prior to designing and building a testbed. This table is taken from a survey paper of ours, with the characteristics extracted from a broad set of existing literature and aligned to testbed objectives, TBO, testbed architecture, TBA, and testbed evaluation process, TBE. The value placed on each characteristic should be driven by end user requirements. For example, the UK Office for Nuclear Regulation provides a set of security assessment principles which operators must incorporate into their systems and processes. This involves a requirement for exercising established processes using live scenarios where practical. Dependent upon exercise aims, developing a comprehensive testbed across each characteristic may not be necessary. For example, where the focus of an exercise is aligned to human response, a testbed's fidelity requirements could be lower than an exercise focusing on the use of security tooling. Once you have an idea on required characteristics, it's time to move on to testbed design and implementation. This can be a challenge, and this is where our model comes in, providing a high-level starting point. In a minute, I'll describe each of the model's layers in relation to the experiment lifecycle. This is made up of 4 key components shown here: design, instantiation, execution, and analysis. These are quite self-explanatory. Essentially, design involves the consideration of core experiment objectives and how the experiment needs to be formulated to support them, including required equipment and associated setup parameters. Instantiation involves taking our initial design and realizing it through the setup of our experimental infrastructure. Execution is where we run our experiment, with analysis taking experiment outputs and examining them to meet our initial objective. If you're more interested in this concept, the publication referenced here provides a more comprehensive overview. So this is our model, made up of 4 independent layers and an infrastructure bridge, with a safety and security wraparound. Starting with the management layer, this acts as a central point from which oversight of a testbed can be established. This includes general functionality from server management to network management, but extends to include the safety and security wraparound. Experiment instantiation and execution is partially covered by this layer. For example, management access to a hypervisor can be used to deploy virtual machines within the experimental layer based on experimental design requirements. Moving on to the user layer, this presents an opportunity to centralize and manage a set of resources which testbed users may require to support experiment design and to capture and analyze experiment data. The functionality of this layer can be viewed as the management of experiment tooling and systems with visibility over the experimental layer. As such, experiment instantiation and execution are also supported by this layer through access into the experimental layer via the infrastructure bridge. For example, this could include accessing, configuring, enabling, and orchestrating the operation of experimental layer devices based on experiment design requirements. The infrastructure bridge simply provides a network infrastructure to control the flow of data between the upper layer and the experimental layer. This can be of benefit when conducting high-risk research within the experimental layer, limiting the spread of malicious artifacts onto the user layer systems. Forming the core element of any ICS testbed is the experimental layer, where all ICS components are deployed, supporting experimental instantiation and execution, again based on design requirements. In addition to ICS, we also consider related and emerging technologies such as building management systems, the Internet of Things, and the Industrial Internet of Things, and so on. Essentially anything encroaching into the ICS space. Finally, based on size and access requirements, a remote access layer can be implemented, accommodating interconnectivity to the management, user, and experimental layers. It is important to note that just like the Purgey model, which, as discussed earlier, is used to compartmentalize core ICS elements into discrete zones, our model layers are not mandatory. The model is simply suggestive, with end users being able to pick and choose capabilities to support their objectives. As we noted earlier with the related work, abstract theoretical concepts can be hard to implement. So what we decided to do was create this figure, breaking each model layer down into a set of practical building blocks. This is to provide a bridge between what can be considered a theoretical concept and practical implementation. Currently, these building blocks are based on the research and experience of those within the Security Lancaster Institute, but we wish to expand these through broader community engagement, which I'll discuss shortly. Using our model and its associated building blocks as a foundational structure, our paper provides practical baseline implementation guidance. Using the ICS building block within our model as an example, we know it will need to consider some form of physical process. This can be achieved through the procurement of large-scale physical systems or small-scale models, such as the 2 pictured on the left from Gunt and Fisher Technic. Alternatively, simulation software may be more appropriate, which can be purchased from companies like Factory.io or self-developed using relevant software libraries. This is a very basic example, But hopefully you can see how the paper has taken an initial starting point with a set of design considerations from our previous work, proposed a high-level model aligned to the experiment lifecycle, logically broken it down into building blocks, and finally offered associated practical implementation options with supporting references. We believe this overcomes the challenge identified in existing work, where information can be either too high level, focused on one implementation approach, or lack sufficient detail for practical application. However, there is still one significant problem that needs to be addressed. As a publication cannot contain a comprehensive overview of all practical implementation options, and it would age over time, we propose a concept of an online living resource. Using our model and current building blocks as a base, we have created a website, which is shown on the slide. This website contains our model with associated descriptions of each layer, current building blocks, and all of the baseline practical implementation options described within the paper. In addition, we've included a broader range of implementation options based on our own research and experience. As our testbed evolves, we will continue to update this resource. However, we believe it provides the foundation for something bigger, a community where others who've also created ICS testbeds can submit suggestions for adding additional building blocks and implementation guidance. Currently, this can be done by sending us an email to the address, which is also shown on the slide. Moving on to future work, to better support a broader level of community engagement, the Security Lancaster Institute is currently building TIDE-H, a threat intelligence data exchange hub. We will look to port our current living resource over to this platform. This will afford us with the ability to build something more comprehensive. We are open to suggestions on what this could look like, perhaps a wiki page or some kind of forum. TIDE-H could also include elements such as configuration files aligned to implementation options or network traffic captures. Again, this is something we want your feedback on. With our current model acting as a foundation, we believe the evolution of its constituent building blocks and associated practical guidance can significantly reduce the barriers faced when building and developing ICS testbeds. But we need help from the community to do this in a meaningful way that is sustainable long term. Thank you for watching. We hope to see you on the 10th, and we very much hope to enjoy your collaboration with the online living resource. Thank you.